In a laboratory in Stuttgart, Germany, light bends in ways the human eye can barely perceive. Thin beams trace invisible paths across mirrors and lenses, each pulse carrying data instead of electricity. At the center of it all sits a tiny chip, humming quietly, a chip that could redefine how artificial intelligence processes information, learns, and scales. This is the work of Q.ANT, an ambitious German startup challenging the foundations of modern computing with the launch of its second-generation photonic processor, the NPU-2. Unlike conventional GPUs, which rely on electrons flowing through silicon circuits and generate heat with every operation, this processor uses photons, particles of light, to perform calculations. Each beam moves at extraordinary speeds, traveling through microscopic optical pathways with remarkable precision. Instead of electrical switches flipping billions of times per second, light waves interact, overlap, and naturally produce mathematical results. To watch it in action is to see information almost dance, flowing seamlessly through a system that operates beyond the physical limits of traditional electronics. In summary, the implications are profound. If this technology continues to mature, AI systems could run faster, consume dramatically less energy dramatically, and scale in ways previously considered unreachable. Data centers that now demand massive power and cooling could become leaner, more efficient, and more sustainable. For now, Q.ANT's engineers work with careful precision. Every optical setup matters. A single shift can disrupt complex computations. Yet progress is steady, controlled, and deliberate. This is not just a new chip. It is a different way of thinking about computation itself. Nvidia remains the benchmark of today's AI infrastructure. But in this quiet German lab, a bold experiment is unfolding, one that could reshape the future of artificial intelligence. Origins and ambition. Q.ANT did not begin as a hardware company chasing market dominance. It began as a research-driven effort to answer a single question: what happens when computation no longer depends on electricity? The company emerged from Germany's deep scientific ecosystem, drawing on decades of photonics research from universities, engineering institutes, and national laboratories. Early work focused not on building products, but on understanding how light could reliably perform mathematical operations at scale. This was unfamiliar territory. Most computing architectures had spent decades refining electronic efficiency rather than replacing electrons entirely. Light does not tolerate error. A fraction of a millimeter shift, a slight temperature shift, or a minor material imperfection could distort an entire calculation. Early systems were confined to laboratory benches, operating under tightly controlled conditions and handling only limited workloads. But the team persisted. Year by year, they refined optical stability, improved signal fidelity, and developed new ways to integrate photonic circuits with conventional electronic systems. What began as abstract theory evolved into functioning prototypes, then into early processors capable of meaningful computation beyond controlled experiments. That journey reached a defining milestone with the launch of Q.ANT's NPU-2, a second-generation photonic processor designed not as an experimental device, but as deployable hardware. This was not a concept demonstration. It was a working system engineered for real-world AI and high-performance computing environments. With NPU-2, Q.ANT crossed a critical threshold from laboratory research to commercial reality and from possibility to proof. How photonic chips work. How do these chips work? Well, most of us think of computers as machines powered by electricity. Inside every processor, electrons flow through tiny circuits, switching transistors on and off billions of times per second. These switches represent zeros and ones, the building blocks of all digital computation. This is how GPUs like Nvidia's perform massive calculations for AI and graphics. Q.ANT's NPU-2 works differently. Instead of relying on electricity, it uses light, photons to carry information. The chip is filled with microscopic optical pathways, mirrors, and waveguides. When light passes through these channels, it naturally performs certain mathematical operations. In other words, the chip doesn't force the calculation. The light itself does the work through its interactions, interference patterns, and direction. This allows the chip to perform calculations in parallel at incredible speed, while generating far less heat than traditional electronic processors. Another key advantage is energy efficiency. Because light can travel without resistance, the NPU-2 consumes significantly less power than GPUs performing the same task. The NPU-2 is also designed for real AI workloads, including complex nonlinear operations that were challenging for first-generation photonic chips. This means it's no longer just a laboratory experiment. Development journey and engineering feats. Building a photonic processor is unlike building any traditional chip. At Q.ANT's labs in Stuttgart, engineers work with structures so tiny that even the smallest vibration, dust particle, or temperature change can affect how light travels. Each optical pathway, mirror, and waveguide must align perfectly. Deviations smaller than a hair can disrupt calculations. Early prototypes were fragile. They could only perform small tasks under tightly controlled conditions, and any error would require hours of fine-tuning. But each test taught the team something critical: how to guide light more precisely, reduce errors, and make the chip reliable enough for real-world AI workloads. Step by step, these tiny victories added up, turning theory into a functioning processor. Collaboration was essential. Q.ANT partnered with Forschungszentrum Jülich, one of Europe's top supercomputing centers, to test how the chip performs on large-scale AI models. The launch of NPU-2 marked a turning point. This second-generation photonic processor is no longer just an experimental device. It's designed to work in actual AI and high-performance computing environments. Potential versus Nvidia. Nvidia has long been the powerhouse of AI. Its GPUs run the world's largest AI models, powering research labs, cloud data centers, and cutting-edge applications. The software ecosystem, developer tools, and infrastructure around Nvidia are vast, mature, and deeply integrated into today's AI landscape. Q.ANT isn't trying to replicate Nvidia, it's taking a different approach entirely. The NPU-2 doesn't rely on electrons flipping transistors billions of times per second. Instead, it uses photons, particles of light, to perform computations naturally and in parallel. This allows certain AI workloads to run faster and far more efficiently than on conventional GPUs. Energy is where the difference becomes most striking. Large AI models today consume megawatts of electricity, requiring huge cooling systems just to operate. Q.ANT's photonic chip uses a fraction of that power. Less heat, less energy, and the ability to scale calculations without massive infrastructure, all of this could redefine what's possible for AI development. Of course, Nvidia remains the standard. Its GPUs are optimized, versatile, and supported by decades of software development. The NPU-2 is still new, and the software ecosystem for photonic chips is only beginning to take shape. Integration with existing AI frameworks requires new tools and adjustments. Yet the potential is enormous. Researchers envision hybrid systems in which photonic chips like the NPU-2 work alongside GPUs, handling tasks that benefit from light-speed computation while traditional processors handle others. For specific operations, Q.ANT's technology could outperform electronic chips in efficiency and speed. The NPU-2 is not a replacement, at least not yet, but it's a serious contender. Nvidia represents the peak of conventional AI hardware, and Q.ANT represents a new path forward. Together, they hint at a future where AI computing may no longer be limited to electrons alone. Challenges and risks. Despite its promise, Q.ANT's photonic technology faces significant challenges. Light-based computation is incredibly precise, and even tiny misalignments or imperfections can disrupt calculations. Scaling production to create millions of chips with this level of accuracy is a major hurdle. Software integration adds another layer of difficulty. Most AI frameworks are built for GPUs. Adapting them to work efficiently with the NPU-2 requires new tools, programming models, and expertise, a process that takes time and investment. Competition is fierce. Nvidia and other chip makers continue to improve electronic processors, while other startups are exploring alternative photonic approaches. Q.ANT must continue innovating to stay ahead, yet every challenge also presents an opportunity. Successfully overcoming manufacturing, software, and market obstacles could establish Q.ANT as a key player in next-generation AI hardware, proving that photonic computing can move from the lab into real-world, large-scale applications. Future outlook and impact. The launch of Q.ANT's NPU-2 is more than just a new processor. It represents a shift in how we think about computation itself. By performing calculations with light, the chip enables AI systems that are faster, more energy efficient, and capable of scaling in ways previously unimaginable. For data centers, this could mean dramatically lower power consumption, reduced heat, and smaller physical footprints. Massive AI models that today require enormous infrastructure could become more practical and environmentally sustainable. Researchers, companies, and developers could tackle problems that were once limited by energy and hardware constraints. Europe's role in this innovation is also significant. Q.ANT demonstrates that the next wave of AI hardware innovation doesn't have to originate solely from Silicon Valley or Asia. Looking ahead, photonic processors like the NPU2 could work alongside GPUs in hybrid systems, tackling specific tasks at light speed while traditional processors handle others. If the technology scales successfully, it could redefine AI performance standards, energy efficiency, and computing architecture, signaling the start of a new era in artificial intelligence. Which part of Q.ANT's NPU2 journey surprised you the most? Was it the use of light instead of electricity, the partnerships with Europe's top research centers, or the potential to challenge Nvidia? Let us know your thoughts in the comments below. Hit like and subscribe for more.